So yeah, elliptic curves. Yeah, there's the QR code if you want to scan it. There's my GitHub as well. I'm not too active right now, but yeah, we just started a new project. We can chat about it later. It's a cool project as well. So yeah, let's start. Elliptic curves. So elliptic curves is a very important cryptographic tool that we use when we calculate cryptographic things or calculations on cryptography, because they provide you a group, and a discrete logarithm is very hard when you use these groups when you calculate your when you do calculations. So Weierstrass form is one of the most common forms that we use when we build our elliptic curves, as you can see here. There's a special formula for that. When you put numbers to A and B, you will get different kind of elliptic curves. But of course, there is one special case. You have to be careful about the singularities, because if you, for example, put 0 to A and B, you will get something we call as cusp, or I don't know, is it the correct way to spell it? Yeah, cusp. And this is something that we don't want, because there's a point that has two same tangent lines. I will talk about the tangent lines, that why we are carrying this too much. You will see in the next few slides, sorry. And if you have A, but the something special that satisfies this function, you will get that we call something that we call node, and you will have a point that has two different tangent line directions, and it's also that something that we don't want. So you have to be careful about this. And after elliptic curves, we can talk about what is field. And field is very important, because we are constructing our elliptic curve over the finite fields. So yeah, finite field is also a very fundamental component that we use in cryptography. It has two binary operators, addition and multiplication. And for example, field, for a good field example, we can say real numbers R is a very good. And if you restrict it in a moduli, you will get finite field. Then you can put that equation, your elliptic curve on this. You can restrict your elliptic curves with this finite field. You will get something like this, for example. So this can be a little bit confusing at first, but here's, for example, our moduli is 19, and you can get at most 18 on an example elliptic curve. So these points are your elements when you use this elliptic curve over this finite field. If you increase your size, for example, this is 97, this is 127 moduli, you will get more and more points. So this is something we want. You have to choose very big moduli to make your discrete logarithm harder, or actually make the try and find method a little bit harder. So people can try every number to find your secret, or whatever you calculated, it will be very easy. That's why we have to pick very big number, and you have to pick prime number, because if you don't pick a prime number for this, for example, in your field, some numbers will have no multiplicative inverse. So it's a bad thing. We want every number to have multiplicative inverse in our calculations. For example, if you have modulo 4, you won't have any multiplicative inverse for 2. There will be no solution for an equation. So we don't want this. Yeah, these points are our results, like our results on elliptic curve, and if we pick them as a set, we will get a group. If it satisfies these five facts, these five properties, we will call them as a group. So what's a group? Yeah, it has only one binary operator, which we call addition. And this addition has to satisfy the closure method, the closure which says that A and B are members of the set. A plus B is also has to be in the set, right? Associativity, I don't know, it's hard to spell. A plus B plus C should be equal to A plus B plus C. And identity, we want an element that we show as 0 here. A plus 0 should equal to A. And inverse says that you have to have inverse for every element that when you add two of them, you have to get identity element. And commutativity says that A plus B should be B plus A. So if you have a set, and if your set satisfies these 5 properties, you will get a group. It's a special type of set. So yeah. So these are, for example, P, Q are our results that when we restrict our elliptic curve, we will get some results. I showed you, if you remember, with dots. So for example, P is a result and Q is a result of this, or sorry, point of this elliptic curve. And if you want to add these 2 points, we have to draw a line on the elliptic curve, and the third intersection point will be our result, but we have to take mirror, like the negate of it on the y-axis, x-axis. So you will, sorry, y, yeah. you will have, like, minus r is your result. So P plus Q is equal to minus r. So this is how we do addition. And what if you want to, for example, double your point, so Q plus Q. So you have to take tangent of your point and just look for the intersection point, and again you have to take the negate of it on the y-axis. So Q plus Q is equal to minus P. So this is how we do double operation or addition to itself. And yeah, there is a case if you want to add P to its negate, which is, minus P, or we show it here as Q, you will get 0. There is no intersection point on this curve, so we call it as 0, point at infinity. So here, the fourth thing that you can do on elliptic curve is if your P is point at infinity, which we call as 0, you can add P to P and you will get point at infinity again, so it will be 0. Yeah. So yeah, there is. So we talked about, for example, Q plus Q. So or P plus P is equal to 2P, right? If you add one more P, you will get 3P. One more P, you will get 4P. So there is something like something more than P, right? You have 4, 5, 6. You have some scalar numbers that we are talking about here, and we have something. Some good algorithm to calculate these 5Ps, 10Ps, or I don't know, millions of Ps. You can calculate it very easily. We will call this scalar multiplication, but technically it's just addition in a very good way, in a good algorithm. So, for example, if you want to add calculate 11P, we have to convert our 11 to binaries, and then if the rightmost is 1, we say, okay, take your P and multiply it with 2 over 0. Then if your second one is 1 as well, your second bit is 1 as well, you say, okay, take your P and double it and add to your P, so you will get 3P, right? And then you take your 2P and double it again, you will get 4P, but the next bit is 0, so we say, no, don't add this. And for the next one, you take your 4P and double it again, you will get 8P, and you can, if you have 1, here we have 1, you can add to your 3P, which you will get 11P at the end. And this scalar multiplication, these scalar numbers, gives us a new field, which we call a scalar field, and if this field's moduli is prime Q, we call this as FQ. Yeah, it is a little bit messy, but here's FQ. Yeah, this add and double is very special algorithm you will see in every calculations in elliptic curves. So yeah, let's talk about ZK proofs a little bit. So basically, if you're attending to these events a lot, you will see ZK. You will hear ZK, I think, a lot. I will just mention it very briefly. Like it's a proof that you don't have to give any information to your verifier. Actually, you have to give, but it's nothing compared to your information. It will be very little, and verifier shouldn't be able to get your secret by given this variables or values. So it allows you to prove something without giving any data to your verifier. It's a very cool method to do. You can say that, okay, I know the solution of this, for example, puzzle or circuit, and the other one won't ask you, the verifier won't ask you for a result. They will just believe you because of this proof, without seeing any solution. So yeah, it's a very cool method. It's a little bit, I think, old now, we can say, right? Compared to the field that we are in. But you will hear a lot about this. So it has some criteria that you have to satisfy. For example, completeness. It says that if your input is valid, your result will be valid for 100%. Like, not 100%, but it's really, really small chance to do something weird in these fields, because the fields that we are inside is 1 over, like, think about 1 over 2 to the 256. So I guess it's like 10 to 80, something like that. And I checked it. I don't know if it's that correct, but I think in the universe, it's the same number, very close numbers in the atom numbers in our universe. So it will be very hard for you to pick some random atom and say, okay, this is your secret, or this is your solution, right? It will be very hard for the calculation. So it's very important for the completeness. If your input is valid, the result will be valid as well. It will always return true. Soundness means that if you have invalid input, if you want to trick someone with your invalid input, you cannot create a valid proof, right? Your result always will be false. But as I told, it's theoretically impossible, because there's a little chance, but it's impossible to get, I guess, right now. For zero knowledge means that you don't have to give any information, so that's what makes it zero knowledge. The verifier won't know your witness values. So yeah, what is witness value? So this is a kind of elements that we, I think, use in zero knowledge. We call this as witness. Witness is your secret information that you don't want to share with your verifier. So if verifier knows that, everyone knows your solution, right? So we call this as witness. We have challenge. You will hear this a lot, I guess, like in the crypto field. There's always challenge. If you are not using snarks, or like you have to communicate with your verifier to get your challenge, give them response back. Response is your response to this challenge. Challenge, like a random number, he will give that, okay, calculate this. If you have the correct witness values, you have to calculate correct result. So he will give you several different challenges, and he will check if he or she will check your response, and if it's correct, then they will accept it. So this is the zero knowledge in a, I think, fast way to explain. And thanks for listening, I guess. Yeah.
Thank you very, very much, Özgür. My duty is to ask the audience if you've got any questions so far, then I can walk up to you. Any questions on ZK? Thanks very much. It was very nice. Questions? Nobody dares to ask. It was very complex, but it was very important.
Maybe I am very good, explaining to.
Okay, so
everyone understands me, sir.
I think that if you don't have or don't dare to ask your question, then you can reach Özgür outside anytime.
Yeah, we can talk about ZK proofs, calculations. I'm okay to it. I can tell about my new project, ZK proofs. I'm okay with it. Yeah.
Okay, so let's give a round of applause to Özgür and Elliptic Curve. Thanks very much.